All right, let's talk about enthalpy. Chemistry is commonly done in beakers out on the desktop or at atmospheric pressure on the counter. And the pressure only changes small increments, so we can say it's pretty much constant pressure. The change in enthalpy, therefore, is the change in the heat at constant pressure. Now, the heat, delta H of reaction is just the heat of reaction. That'll tell us whether it produces or consumes heat. Remember, delta H is negative, means it's endothermic. Positive means it's endothermic. And so our heat of reaction can be the enthalpies of the products minus the enthalpies of the reactants, or substances produced minus substance consumed, or in general, final minus initial. Now, how do you calculate that heat at constant pressure? It's calorimetry. One way of doing that was a simple coffee cup calorimeter, because the styrofoam in the coffee cup is an insulator. It keeps a lot of heat from going in or out of the container. And we can use that to measure the heat at constant pressure of a exothermic reaction in particular, but you can with some endothermics as well, depending. So you got the insulated cup. Sometimes if you double cup it, you get a little insulating layer of air, so that helps. You've got a lid where you can put the thermometer in and measure, a little stir. And what you're going to do is generate heat. If you know the mass of the water, you can calculate how much heat is being produced in the container. But it's open to the atmosphere, so it's constant pressure. So if an exothermic reaction is produced in the calorimeter cup, then the heat evolved by the reaction will be absorbed by the water. So I would get a net temperature increase of the water, because the reaction is releasing heat and the water is the immediate surroundings. But some of the heat is lost to the surroundings, where the amount of heat released by the reaction is going to be the amount of heat absorbed by the calorimeter itself, plus the amount of heat absorbed by the solution. So you're counting for the amount of heat you lose. And that's called the heat capacity of the calorimeter, that amount of heat you'll lose. And I'll show you how to calculate that. Now, the energy unit that we'll use primarily is the joule. We compare that to the older energy unit of the calorie. 4.184 joules is 1 calorie. 1 kilojoule is 1,000 joules. A kilocalorie is 1,000 calories with a small c, or 1 food calorie, which is calorie with a capital C. So if you're counting calories for your diet, those are capital C calories, which is 1,000 of the little c calories. The little c calorie is defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, the specific heat, which is going to be a quantity we're going to use in our calculations, is the quantity of heat required to change the temperature of 1 gram of any substance by 1 degree Celsius, and you'll have to look that up for most things. Now, specific heat of water in joules is 4.184 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. And lead is 0.128 joules per gram degree Celsius. Notice that specific heat for water is high. And that explains why we retain our body temperature, for example. You have to remove or add a large amount of heat to cause a significant temperature change compared to some other substances. But we can calculate that heat gained or lost using the equation Q equals mc delta T, where Q is the heat expressed in joules or calories, M is the mass in grams, C is the specific heat in joules per gram degree Celsius, or calories per gram degree Celsius, and delta T is the change in temperature in degrees Celsius. That brings us to our problem. We want to calculate the specific heat of a solid in joules per gram degree Celsius and in calories per gram degree Celsius if 1,638 joules are required to raise the temperature of 125 grams of the solid from 25 to 52.6 degrees Celsius. Okay, so now we're going to look at a particular problem where we got Q equals mc delta T, and I've written the values of each of the things over there. What I'm solving for is the C, the specific heat. Don't confuse Q and C. Q is heat, C is specific heat. And you need to make sure you keep those straight. It's a common mistake to get them backwards. So C equals Q divided by M and delta T. So I've got the Q, I've got the M. I need to subtract these two to get the delta T. So delta T equals 52.6 degrees Celsius minus 25.0 degrees Celsius, or 27.6 degrees Celsius. Now we've got everything we need. We got 1,638 joules divided by 125 grams and 27.6 degrees Celsius. Then we're going to get 0.475 joules per gram degree Celsius. So that's one of your answers. It asks for it in calories per gram, so I could do this whole thing again in converting my energy units, or I could just convert the answer, which is what I'm going to do. 0.475 joules per gram degree Celsius. All I need to do is convert the joules to calories, and as we mentioned before, there's 4.184 joules per 1 calorie. Joules will cancel, and you're left with calories per gram degree Celsius. And so that's going to be 0.113 calories per gram degree Celsius. And then that is, in fact, your answer. Okay, so if we got 50 grams of hot water at 90 degrees Celsius, add that to a calorimeter cup containing 50 grams of room temperature water at 24 degrees Celsius, the resulting mixture reaches a temperature of 42.5 degrees Celsius. We want to calculate the heat capacity of the calorimeter cup in joules per degree Celsius. And the specific heat of the water is 4.184 joules per gram degree Celsius. This is what I was talking about, where the calorimeter cup is losing heat. Because if it hadn't lost any heat, it should be the average of the two starting temperatures, or 57 degrees Celsius, but we only made it up to 42.5, so it is definitely losing some heat. All right, let's take a look at this problem. I've transferred all the information from the problem. We got the masses of the hot and the room temperature water, the hot and the room temperature and the final temperature and the specific heat of water. We need those delta T's. So delta T for the hot water equals, we're just going to absolute value this because we're talking about heat lost and heat gained specifically. So it'll be 42.5 degrees Celsius minus 90 degrees Celsius absolute value. And so we're saying that the temperature drops by 47.5 degrees Celsius. The room temperature water is going to also end at 42.5 degrees Celsius minus 24.0 degrees Celsius. Again, absolute valuing, we get 18.5 degrees Celsius. Now let's calculate the heats. So we're going to say the heat lost by the hot water is still going to be MC delta T. So we got 50 grams, 4.184 joules per gram degrees Celsius, and then 47.5 degrees Celsius. That's going to equal 9,937 joules. So now we're going to measure the heat gained by the room temperature water, still MC delta T. So we're going to do our 50 grams again, our 4.184 joules per gram degrees Celsius, and then 18.5 degrees Celsius. It's going to be 3,870 joules. Now, if we take the difference in those two, we're going to get 6,117 joules. This is the amount of heat lost to the calorimeter wall and not gained by the water. Again, particularly inefficient calorimeter, but we're kind of doing it a bad one to kind of make a point. And so then what we have to do is we have to figure out that calorimeter constant. So our calorimeter constant is going to equal the heat absorbed by the calorimeter wall divided by the change in the temperature of the room temperature water. So we're going to say 6,117 divided by the 18.5 degrees Celsius. And so that would mean we'd have 331 joules per degree Celsius. And what that means is for every 1 degree temperature increase inside the calorimeter cup with an exothermic reaction, we would lose that much heat to the calorimeter cup or the surroundings at large. So that would be our answer to the first part. Now in this particular problem, we're going to use the calorimeter cup we already calibrated. Notice this is a part B. So now if we take 50 milliliters of 1 molar HCl and react that with 50 milliliters of 1 molar sodium hydroxide, and that same calorimeter cup rises from 24 degrees Celsius to 30.1, we're going to assume the specific heats are close to that of water, which is 4.18 joules per gram degree Celsius, and that their densities are 1 gram per milliliter, which means be 50 milliliters plus 50 milliliters is 100 milliliters. And since the density is 1, we'll say 100 grams of total mass. We're going to calculate the molar heat of reaction in kilojoules per mole. Okay, this next part is really a part B, so I'm still showing you part A. We're going to use that calorimeter constant from this first part in this second part. So I'm going to push that on up so you can see the rest of the paper. And we're going to try to work that. So again, we need our delta T. So that's going to be 30.1 degrees Celsius minus 24.0 degrees Celsius equaling 6.1 degrees Celsius. Now, our heat is going to be Q equals MC delta T plus the amount of heat our calorimeter is losing. That's going to be our calorimeter constant times delta T. So Q equals 100 grams of total solution. That's 50 for each, so a total of 100 grams of solution. Time specific heat 4.184 joules per gram degree Celsius times the change temperature 6.1 degrees Celsius plus our calorimeter constant 331 joules per degree Celsius times our 6.1 degrees Celsius. So our Q then is 4,571 joules. Now if I want the heat in kilojoules per mole, I'm going to need to take it one more step. The heat of reaction is going to be negative Q to get the sign right, divided by the number of moles of the limiting reactant. In this case, we had both had 50 milliliters and 1 molar, so our moles is going to be 0.05000 liters times 1.00 moles per liter. So our moles is 0.0500 moles. And so now we can plug in chug, so negative. And now we're going to need it in kilojoules, so we're going to take 3 places off of that and say 4.571 kilojoules divided by our moles, 0.0500 moles, which would give us a negative 91.4 kilojoules per mole, where that is our answer. And that looks more like what you're used to seeing for kilojoule per mole problems. Another thing you can do with calorimetry is determine the specific heat of something using, say, water as a reference, since I know the specific heat of water. So in this case, you take metal pellets which you've heated in a test tube. Mainly, you heated it in a hot water bath inside the test tube so the pellets would stay dry and you'd have a consistent mass of everything. Then you dump those pellets into a calorimeter cup containing a set amount of water, measure the temperature increase of the water, and then if you assume heat lost equals heat gained, you can calculate the specific heat of the metal in this case. So here's a particular, for instance, if we got 11 grams of hot lead metal at 100 degrees Celsius, so we heat that up in a boiling water bath inside a test tube. We pour that metal into a calorimeter cup containing 25 milliliters of water. We'll assume 25 grams of water, and we want to specific heat of the lead if the temperature rises from 25 to 26 degrees Celsius. So we'll need to set up some equations. All right, so let's look at our problem that we have going on. And we can see that we've got the mass of lead metal, mass of water, change two temperatures from water, and then the metal will go from this to this. And what we're going to base this on is that the heat mass, the metal, the heat's lost is equal to the heat gained by water, but they're in opposite directions, so you'll get a negative sign in the formula. And so the change in temperature for the water is pretty straightforward. 26.0 degrees Celsius minus 25.0 degrees Celsius equals 1.0 degrees Celsius. Change in temperature for the metal is going to be 26.0 degrees Celsius minus 100 degrees Celsius, or a negative 74.0 degrees Celsius. Now, what you can do is, since you get a negative sign in the formula and a negative temperature, you could just positive them both out and not carry on that negative sign the whole problem. So substituting, we're going to have mass of the metal, specific heat of the metal, change in temperature for the metal equals mass of the water, specific heat of the water, change in temperature for the water. And we've got this one. What we want to find is that one. So specific heat of the metal is equal to mass of water, specific heat, water, change in temperature, water, divided by mass of the metal, change in temperature for the metal. And then it's just plug and chug. The water's mass is 25.0 grams. Specific heat of water, we know, is 4.184 joules per gram degree Celsius. We've done that in a couple of problems already. Change in temperature of the water is our 1 degree. Mass of the metal is 11 grams, and the change in temperature of the metal is 74 degrees Celsius. So then it's just a matter of canceling our units out, and we're left with joules per gram degree Celsius. So the specific heat of our metal is going to be 0.13 joules per gram degree Celsius. And that would be the specific heat of our metal.